Hi there, and welcome back to this third part of our series where we will be exploring the mathematics of elliptic curves and answering the questions, what is a private key and what is a public key? And of course, we'll have to know what an elliptic curve is. Now, I just want to be transparent here, as this image sort of is implying that this section is really meant to be visual and conceptual. I just want to give you enough elliptic curve intuition so that you're going to be able to understand what a public and private key is. This is not the full level of mathematical rigor and detail that is used in the actual implementation. And with that being said, let's go ahead and take a look at our elliptic curve. So we can see a plot, and here is the equation of our elliptic curve. We do have these parameters a and b, which are used to describe specific elliptic curves, and these will be given to us. Just a little bit of review here. The x-axis serves as an index of all the possible values that we could use to replace this variable x placeholder in our equation. And that vertical axis, the y-axis, again is just an index of all the possible values of y that we could replace our y placeholder variable in our equation with. Now, a point is described using an ordered pair, and it's ordered for a reason, because the first element is always the x coordinate, and it describes the horizontal position of our point in the plane. The second component, the y coordinate, is used to describe the vertical position of the point. And together, they are able to describe the position of our point in the plane. Now, going back to our equation, this is a boolean statement, meaning that it is either true or it is false. Now, if we were to choose a value of x and a value of y, and then evaluate both the left and right expressions and get the same values, then we would say that our equation is true. And we actually have a point. We have an x and a y value. That x coordinate tells us the horizontal position of the point, and the y coordinate tells us the vertical position. And since our equation is true, this point will exist on the curve. Now, if we were to have chosen, again, some value of x and value of y, but this time when we evaluated the left and right expressions, we got different values, our equation would be false. Now, we did use an x and a y value, which we could describe as a point. Again, the x coordinate gives us that horizontal position, and our y coordinate gives us that vertical position. And together, they describe the location of this point in the plane. And since it gives us an equation that's false, this point is not on the curve. What I'm really trying to get at here is that this curve is visualizing all the points that make this equation true. So what do we have so far? Well, we've just created a plot of this curve, which is made up of points. And these points form a set. So I have a group of objects which are points. And now I want to do something with those objects, with those points. So I'm creating an operation. It's a binary operation because it's going to have two operands, two inputs. And I'm even going to give it a name. I'm going to call it circle plus. I don't know what it does yet, but I do know it's going to give me some form of result. Now, there is an interesting property of this type of curve, which is if I were to draw a non-vertical line through the curve, it will intersect at 3 points. And this is really interesting because if I go back and look at my operation, how many objects do I have? I've got 3. I have 2 operands and a result. So if I were to use one of those points as my first operand and the second point, a second operand, I could use the definition of my operation to be drawing a line between those 2 points and finding that intersection point. I've got myself an operation. Now, it turns out for our protocol, we're going to need an algebraic structure called a group. So we have to make sure that it is able to satisfy the following requirements. Now the first one, closure, is actually pretty easy to show. This means that my first operand, the element, which is our point, needs to belong to this set of points. And this is true because it's on the curve. And then my second operand, which is that red point, it also needs to be a member of this set of points, which it is because it's on the curve. And the result itself also needs to belong to this set of points. And again, we can visually see this because it is on the curve. So the next requirement is going to be this inverse element. So let's go take a look at that next. So we're going to start with something that we already feel a bit familiar with, which is the operation of addition with numbers, which does have something called an inverse. So if I have a plus its additive inverse, negative a, this will result in the identity element, or the additive identity 0. So for example, if I have 5, its inverse is negative 5, which produces the identity element 0. And what I want is to create something similar for this circle plus operation. I want an inverse. Well, we are working with objects that are points. So I'm going to start off with my first operand being a point on our curve. So to create this inverse, I'm going to get some inspiration from the additive inverse. And if we take a look, we have our identity, and the additive inverse of A is symmetric about the identity. So there's this idea of symmetry. And if we look at our elliptic curve, it is symmetric about the x-axis. So a really good place to look for this inverse is the reflection of p in the x-axis. And so we are going to try this negative p as our inverse element. The negative just means inverse. All right, let's try our operation. I'm going to go p, circle plus, negative p. So I'm going to draw my line between the points, and well, I need a third point, don't I? So I'm going to create one. I'm just going to call it O. So this is, I know it's not on the curve, but I'm just going to try it out. Now let's try this again. I'm going to try it with another point. Let's call this one Q. And then we are going to have an inverse for Q, which will be negative Q. And again, we would need to try our operation here. So drawing our vertical line, but then what would this point be? And notice that these are parallel lines, and I want you to think iceberg for a moment. Now we're going to take a look at a set of railroad tracks. Now we know that these rails are parallel, but we can visually look at this, and from our perspective, they are converging at some point way far in the distance. And this is what I'm going to call our infinity point. This is that point O that I've been talking about. So we are actually going to take what we perceive seriously. So we have this point O now off in the distance, our infinity point. And since these two lines are parallel, they should converge to this point O, meaning that I really have a strong contender for an identity element because all these parallel vertical lines should intersect at this point O. All right, so at this point I have possibly negative p as my inverse element, but I'm really not sure this is true because I don't quite know if this point O is my identity element. So we're now going to need to take a look at our identity. Again, we're going to turn to the additive identity where we have A plus its additive identity, or identity, which is 0, and notice that A maintains its identity. Again, for example, 5 plus the additive identity 0 gives us 5. And what we want to show is that P, circle plus, our identity, is P. Well, we already have our point P, negative P, its proposed inverse. We do our operation and we have this proposed identity O. So let's try it out. We are going to take that point P and we're going to do our operation, circle plus, and our point at infinity, our infinity point, our proposed identity. But what's the other point on this line? It's negative P, and the identity element is failing us. Now it turns out we can fix this. And to do this, we're going to go back and take a look at our operation. So if we were to have some point N on our curve and we were to circle plus another point Q, we know how our operation works. We would draw a line between the 2 points and find the intersection point. What I'm proposing we do is we extend our operation. We add one more step. We take that point of intersection and find its inverse. So we're reflecting it in the x-axis. And what does this do for us? Well, if we take a look at our operation now, we are going to get the same result as before, which is our intersection point, but then we're going to need to reflect it in the x-axis. So when I substitute our negative P in here and then reflect it in the x-axis, what do we get? We get P. And now we can see that our identity element works, our inverse element works, super fantastic. Now I talked about the iceberg, and showing that this is associative is really tough. So I'm just going to tell us now that associativity and commutativity hold. And so we're going to get this group structure. And the reason why I showed you this is just so that we could get a feeling for this operation of addition. In fact, we now have something called an additive group. So we are going to upgrade our symbol to a plus sign. And in fact, let's just go ahead and call this the operation of addition. So why did we do this? Well, we are going to want to do 2 forms of addition. And we're going to get started with a point, G, that both Apple School and Business Manager and we are going to know. And it is common knowledge, we both know about this point G. And what we want to do is to take that point G and add it to itself. That's hard, isn't it? Because our operation involves 2 points. So we're going to be a little bit creative here. I'm going to choose some point that is not G, but it's close enough, and we're going to do our operation. So we draw our line through the points, find the intersection point. Now that's definitely not 2G. So I'm going to choose a point that's closer to G. I'm going to draw a line through my 2 points and then find the intersection. That point is actually closer to 2G. I'm going to do that again. I'm going to pick a point even closer to G. Draw my line between the 2 points, find the intersection. Now, notice that I'm ignoring the reflection right now, just as we try to conceptually understand what's going on as we try to find this second point, G. So we want to get as close to G as we can. So again, line through the points, finding the intersection point. And in fact, we can get as close to 2G as we want by making this point close enough to G. And now what we're going to do is you can almost think of it as taking G and then putting another point G on top of it. And we're going to construct something called a tangent line. Tangent meaning touching. So this line is just touching the curve at one point G, but it gives us an intersection point, and then we can go ahead and reflect that and get our result, 2G. So we now have something called point doubling. The next thing we want to consider is adding 2 distinct points. And this is in fact easier. So we already saw that we could take a point G, add it to itself to get a point 2G. Now what I'd like to do is take 2G and add it to G. Well, we can just use our operation. We are going to draw a line between 2G and G, find the intersection point, and remember, we need to reflect this in the x-axis so that we hold our group operation. Now that we're at 3G, we're going to do it again. I'm going to take 3G, add it to G by drawing a line through the 2 points, finding the intersection point, and again, reflecting so our group structure holds. Now, there are equations to be able to do this process, And in fact, neither the geometric or the actual equations are used in the actual implementation. We've actually got some really fast algorithms for this, but I just want you to visually see how we're adding points. So why have we done all this? Well, we are interested in understanding what the public and private key are. Again, we share that point G between us and Apple School Business Manager. And we are going to start taking G, adding it to itself to get 2G. And we saw we could get 3G, 4G. So we could increment this value of G. So we keep adding G to itself. And we can do this for any positive integer. But there's one integer that's very interesting, which is our private key. If we take G and add it to itself, private key number of times, we will get the point, our public key. So the private key is just a positive integer, and our public key is just a point on the curve. So when you created that API account, essentially what you did is Apple School Business Manager took G, added it to itself, private key number of times, which resulted in a public key. That public key is going to be used to verify our signature, and the private key that we downloaded is going to help us construct the signature using our signature forge function. Now, if you're looking at this equation, you're probably thinking, well, if we know the public key and we know G, wouldn't it be easy to get the private key just by dividing both sides by G? Well, remember, we're not working with numbers. Those are not the objects. We are working with objects, which are points. And it took us a while to define our operation, circle plus, which allowed us to take a point and add it to itself, private key number of times. And what we don't have here is an operation of multiplication, which implies we don't have an operation of division. So there's no way for us to easily recover that private key. This is a really tough problem, and it's a form of what is called the discrete logarithm problem. And this is what's really, 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 really tough in keeping that private key safe. Now, in the next video, we are going to move on and talk about a special type of function called a hashing function. So we'll see you in the next video.